Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Photographic. We'll look at some aspects of digital image processing. When I'm prepping an image to use, I'll often use a sharpened tool to try to improve the image. And of course, when the image is saved, it's typically compressed as a JPEG file to save space. We'll get some insight into how these operations can work. Remarkably, our starting place will be the same mathematics developed in the musical episode. Fourier series, the foundation for music synthesis, is also a basic tool for image processing. Fourier series takes a given function and rewrites it as a sum of sine waves, identifying the right combination of frequencies to make the desired function. For music, the function is the sound waveform. For photographs, the function is the color information for the pixels. A simple but important example is the square wave, which alternates between values of 0 and 1, or any other pair of values like -2 and +2 in the graphic shown. It turns out that this can be written in the following way. Here are some graphs as we include more and more terms of this series. Notice that even with only 10 terms, the approximation is very good in most places. The inaccuracies near the jumps will be important later. Let's talk about an image that is 1,000 by 1,000 pixels. Each pixel has an RGB level, the intensity of red, green, and blue tones that make up that pixel. You can think of the set of red levels, for example, as function values for a function of two variables, horizontal and vertical. This function gives rise to a Fourier series, a combination of sine waves in each of the two directions, sine x times sine y, for example. We find the Fourier series for each of the three primary colors and then add them together. This may sound complicated, but look at the storage requirements. Storing each of the RGB values for each of the 1,000 by 1,000 pixels adds up to 3 million numbers. A sharp image using, say, 10,000 terms for each Fourier series requires 30,000 numbers, just 1% of the original 3 million. So Fourier series allows for large image compression possibilities. Let's see what this looks like in action. The target picture looks like this. Using just two frequencies in a Fourier series produces this image. Not recognizable, but if you think about it, remarkably close to the target image using just 6 numbers. Let's bump it up to 10 frequencies. It's a lot better, though it's still very blurry, and there are noticeable waves coming off the black coat. Here's what we get with 75 frequencies. Not bad at all, especially given that the storage requirement is less than 0.2% of the original. If you look closely at this picture, we can see waves coming off the black coat and in between the two heads. This has nothing to do with the magnetic aura of the two people, but it is a flaw in Fourier series. It is especially annoying in the jet plane image here. The image on the left is a badly blurred photograph with the digitally sharpened image on the right. Impressive clarity, especially if you need to determine friend or foe. But we got some strong ghost images around the edges. The Fourier series characteristic is known as the Gibbs phenomenon and can be seen in this image of a Fourier series approximation in blue of the square wave in purple. Notice that when the Fourier series needs to jump from 0 to 1 or from 1 to 0, it has an overshoot-undershoot at the edges. In the photos, you could think of black as 0 and white as 1, and the shadow or wave is this same overshoot-undershoot starting at the edge of a sharp black to white transition. Fortunately, there are modifications to the Fourier series that remove the Gibbs phenomenon. Here is the sigma-corrected series with 75 frequencies. Not as sharp as before, but no ghostly waves, and still highly compressed from the original image. So we can use mathematics to reduce storage requirements substantially. How could we sharpen an image? Before there was a sharpen button in Photoshop, I could sometimes make improvement just by increasing the contrast. And this is the basis for how the sharpen command works. That is, a sharp image has very abrupt, sharp changes from light to dark, or in switching from one color to another. In terms of a sine wave, the higher the frequency, the faster the wave changes from maximum to minimum, so you can get a sharper image by adding in more high-frequency waves or by increasing the intensity of the high-frequency waves present. For the square wave, you have much sharper edges with higher frequency terms added, though if you look closely, you can still see a Gibbs phenomenon. A music equalizer gives you control over the intensities of the different frequencies in your music. You increase bass by bumping up the low frequencies, or increase treble by cranking up the higher frequencies. This gives us a very interesting analogy. Increasing the treble is mathematically similar to increasing the contrast and sharpening an image. I love it when math brings to light connections between seemingly diverse topics.